When many people think of groundwater and wells, they may think of the old-fashioned dug wells. You know, the one where somebody falls in and has to be rescued. In times now mostly past, there are dug wells still being used. A well digger would dig a hole down to the water table, secure the walls of the base of the hole with rocks or blocks, and then dig down further, below the water table, until he couldn't dig because of the inflowing water. He would then build a circular wall up to the land surface where carpenters would build the wellhead. Of course, the deeper the hole, the better, so the best time to dig such a well is when water tables are low. Dug wells are only rarely constructed now. They don't yield a lot of water. They go dry with small fluctuations of the water table. They are easily polluted, and they really are dangerous. Animals and kids really do fall in them. So instead, groundwater is mostly obtained through drilled wells, which are far more narrow, only 6 to 18 inches wide, and are much deeper. In most places, properly designed well systems can supply abundant amounts of good quality water while being both consistent and safe. The days of getting water from a dug well are best left to the movies, stories, and nursery rhymes. Groundwater is one of the most important geologic resources that we use. About half the drinking water in the United States comes from groundwater, and in rural areas, almost all drinking water is sourced in groundwater. Although drinking water is one really important use of groundwater, a larger and growing proportion of groundwater, roughly 2/3 of all groundwater pumped annually, is used for irrigation. Groundwater is also used for industrial purposes. And besides all the human uses, groundwater recharges or replenishes lakes, rivers, and wetlands when there isn't an abundance of rainwater. The reason rivers keep flowing during periods of drought is because groundwater is flowing into them. That's interesting, right? How would you find where that happens? If you walk in a small stream in the summertime, the place where the water suddenly gets cold is where groundwater is flowing into the stream. Or sometimes you might notice fish congregating in these areas because there is more oxygen in the cold water. Yet with all of its uses, groundwater and groundwater wells are not well understood by the general public. This is a dangerous situation. Groundwater is one of those things that you never really appreciate until it's gone. Liquid fresh water on Earth is overwhelmingly stored as groundwater, 94% of all liquid fresh water. The fresh water we notice above ground is only a tiny amount. Lakes account for less than 4% of Earth's liquid fresh water. Soil moisture accounts for another 2%, and rivers account for less than 1/10 of 1% of liquid fresh water. So what is groundwater? Not all water on the ground or even in the ground is called groundwater. Groundwater is the water obtained from a saturated and permeable subsurface layer below the soil. The important thing to remember about groundwater is that it saturates the small openings between rock sediments and in small rock fractures. Those small openings and fractures in the rock are called pores. If a geologic unit has enough saturated pores that yield an economically viable amount of water, it is called an aquifer. So the term aquifer really is an economic term. Exactly what is called an aquifer will really vary from place to place. Because water flows through pores, groundwater movement is called porous media flow, and I'm going to demonstrate that for you now. In essence, what I'm about to show you is everything you need to know about groundwater. So I have a rock, but this is no ordinary rock, not because of the rock type. It's just a sandstone, similar to sandstones that occur throughout the United States. This one happens to be the Jordan Sandstone, a rock one can find in southern Minnesota and Wisconsin, among other places. It's the type of sandstone that's referred to as ultra-pure sandstone because it is almost entirely made up of quartz. There is a little secondary cement holding it together loosely, but you can see the grains scrape off my hand readily. But I've taken this ordinary sandstone and carved out this totally cool bowl in the top of it. This way, I can eat all kinds of things in an earthy way. I told my kids it was for my Flintstone dining theme. Great for eating the paleo diet and Cro-Magnon dishes of all types. Let's pour water in it. Before I do, I want you to know a couple of important things. One is, this sandstone is a solid rock. The individual sand grains that make up this rock are packed together as closely as they can be packed. But still, there's a substantial number of pore spaces. In fact, the rock has a porosity of 30%. To emphasize how much pore space there is, I like to tell students that if I threw this rock at them, in addition to ducking, they could also hope that they get hit by the 30% of the rock that is air. There's a lot of pore space. So let's compare the volume of the rock to the volume of water I'm going to put in it. The water volume in this container is going to equal about 30% of the total volume of this rock. In this particular case, it is going to be about half a liter of water for this rock. I'm going to pour the water into the bowl here. It's obvious, of course, that the water flows quickly out of the container. Equally quick is how the bowl is filled. Now wait a few seconds. What's happening? Well, let me show you. Oh! Where's the water? Of course, what happens is the water infiltrates in the rock. Let's pour some more water in. What do you see? The more water I pour in, the darker the rock gets. What you're seeing is the pores filling with water and the rock becoming saturated. Let's pour in even more water. At a certain point, the rock will become fully saturated. Notice what's happening as I poured more water into the bowl. It infiltrates at a slower and slower rate. The rock is saturated, so there's no place for the water to go. Water is now leaving the rock. What's important here is that the velocity of the groundwater flow, the water flowing into the rock from the water bottle, is pretty fast. Remember, a river in nature is moving at a rate of miles per day. But the groundwater movement, my hand's wet, through sandstone is very slow, moving at a rate of only inches per day, only 1/100th of a single mile per year. This is a very slow process. So that's porous media flow. Water infiltrates into the ground and the rocks. It makes its way around particles and into pore spaces, eventually flowing out into a well or onto the land surface as a river, lake, wetland, or spring. It's estimated that groundwater supplies 40 to 50% of the water in small or medium-sized streams. This is the disconnect between the science of porous media flow and the general public knowledge of groundwater. I teach an entire course about groundwater. And when people find out, they invariably talk about their perceptions of groundwater. Many, many times, those perceptions are completely false. Let's talk about a couple. It's common for people to believe that water coming from the ground, either as a spring or from a water well, is pure water. Advertising will even claim some companies' bottled spring water is as pure as whatever word they feel like using. Adjectives like natural or clear or pure really don't mean anything on a water label. These are strictly terms used in advertising to convince you of the product's quality. Think about the water I poured into this rock. The water that comes out as groundwater, you could even call it a spring, is essentially the same quality that I poured in. There's a little calcium carbonate cement holding the particles of sand together, so you might get a little bit of calcium carbonate in the water that's dripping out. By the way, that's the origin of hard water. Calcium carbonate and other rocks get dissolved into water. But essentially, the water that went in is the water that is coming out. Something to think about is, what if I used polluted water in the demonstration? Well, in some geologic settings, pollutants may be filtered out or will break down in the water depending on the porosity of the rock. But all too frequently, pollutants that enter the ground stay in the groundwater. Why is that? Groundwater is part of the hydrologic cycle we talked about early in the course. Groundwater is connected to all other water bodies on the land surface. If rainfall is polluted and it infiltrates into the groundwater, then the groundwater will be polluted. Now, material that is sandstone or sand can very slowly purify water. Groundwater, inching along through sandstone, moving for months or more through sandy materials, can shed pollutants such as sewage. But you don't know if that's happening when you see a spring. You need a natural system that has very slow groundwater flow rates. A second misconception I hear is people talking about a well accessing an underground lake or an underground river. Usually this is in the context of people talking about either how lucky they were to find water or the great quality of the water that's coming out of the well. But what have we already said? Groundwater is water that saturates porous media, like my sandstone. Groundwater doesn't occur as an underground lake or an underground river. When you drill a well, you're intersecting small openings in the rock pores. If you intersect enough pores that are filled with water, then you will generate enough water flowing through the pores into your well to supply whatever water needs you have. I understand that under unique conditions, for example, caves or sinkholes, that you can find underground bodies of water. But that's not where drinking water sourced in groundwater comes from. And yes, there are all sorts of myths and stories about mysterious underground passageways and rivers. The River Styx is an example. But those are all just stories. If you could take all the tiny underground pores across the United States, all the tiny openings in rocks, like this example of the Jordan sandstone, and could combine them to make one single large opening, that opening would be 190 feet tall under the entire continental United States. That's how abundant the void space is in porous rocks. And that's why it's enough to supply drinking water. Look once more at this rock. It's getting darker. There are no underground rivers. There is no underground lake. It's a solid rock. But it is about 30% pores. And because this geologic unit is so large, it makes a great aquifer. One last thing that people tell me is that they knew a guy who could find water using, you name it, forked sticks, metal wires, some kind of family heirloom, who knows what. You cannot find groundwater with a stick. There's simply no physical law to justify such a process. Just think about this rock in a demonstration. At this point, every single pore space in that rock is filled with water. Rock spaces are filled with water the same way all over the planet. In fact, that's the definition of the water table, the point below the land surface where every pore is filled with water. I could claim to have a magical coin for finding water, but there is water almost everywhere. So if I flip the coin here, it's going to land where there is water below it. If I flip the coin here, again, there is water below it. Someone claiming to find water with a dowsing rod is simply finding what anybody could find by tossing the stick over their shoulder. There is water almost everywhere. So why does this idea of dowsing persist? Well, it's something that's been done for hundreds of years, and it's virtually impossible not to find water. The stick goes down, the dowser says dig, and you hit water. But there is water almost everywhere, so the method appears to be a proven success. And if the dowser site does not yield water, then they declare that there is no water around. But it's the drilling that has already proved that. The dowser offers no real insight, yet cannot lose. Just find a good well driller. Now let's talk about how a well actually works. A water well is simply a hole that intersects the water table. That's any geologic unit that is both saturated with water and permeable to water flow. As I mentioned, you can dig the hole yourself if the water table is not too far down. Many folks will excavate a small well and use it for a pond or some lawn ornament. But in places where the water table is deeper than 5 or 6 feet, hand digging a well is a labor-intensive and dangerous job. Rocks falling or the hole collapsing are serious threats to safety. It's also cold. Anywhere below the so-called active layer of freeze-thaw, below 4 or 5 feet, you're at average annual temperature for your location, which is only 34 to 50 degrees. Digging for any period of time will get cold. Instead, let's think about drilling a well. Here's a cross-section of the Earth near the surface. Hydrologically, the subsurface is divided into an unsaturated zone, and below that is the saturated zone. The top of the saturated zone is called the water table. The unsaturated zone includes water in the soil and water that is in the process of percolating downward towards the saturated zone of the water table. The bottom of the unsaturated zone is known as the capillary fringe. This is a zone right above the water table where some water is moving upward due to surface tension. Throughout the unsaturated zone, there are some pores and cracks that do not contain water. As a result, oxidation is also occurring and various chemical processes are at work. Simply drilling into the saturated zone doesn't ensure that the geologic units will produce sufficient amounts of water. It depends on porosity and permeability. Because of the variability in rocks and rock types below the ground surface, a well driller may encounter a geologic unit that has relatively little porosity, and a scarcity of pores means it does not contain much water. Most metamorphic rocks have low porosity. Most igneous rocks, like the granite all over New England, have almost no porosity. The only hope for water there is if the granite, throughout geologic time, has been fractured. Fractured are called secondary porosity. Another problem is geologic units with low permeability. Water cannot pass through them. Shale is a porous sedimentary rock that lets moisture in. That's why there's so much oil in oil shales. But shale is impermeable, meaning that the pores are not connected enough to allow liquid to flow through. That's why extracting oil from shale requires so much more energy. Shale is porous, yet impermeable. Clay, which is the sediment that makes up shale, has very similar properties. Again, clay lets in lots of moisture, but the pores in the clay are so tiny that they cannot let liquid pass through. If you ever step in the muddy, clay-rich bottom of a lake or swamp, you can experience this firsthand. Your foot quickly sinks into the mud because 50% of the substrate of mud is pore space. It won't support your weight. At the same time, your weight displaces anything that was in those pores. It can be water, but can also be gases that are produced by decaying organic matter. Because the clay is impermeable, the gases are trapped until your sinking foot releases them. Oh, that sweet smell of lake mud sulfur. Groundwater hydrologists call this impermeable unit a confining layer. Confining layers can prevent the passage of pollutants into underlying aquifers. These underlying aquifers are called confined aquifers, and they frequently have very good quality water. Sometimes the confined layers are so completely confined that the groundwater in those confined aquifers is under pressure. This is due both to the weight of the overlying rocks and the slope or dip of the geologic units. This is called an artesian aquifer. In especially remarkable situations, the water in confined aquifers can be under such high pressures that once a well is drilled, the water will flow out of the well higher than the ground surface. An aquifer with the water under this kind of pressure is called a flowing artesian aquifer. It's a remarkable thing to see. Let's get back to the water in the well. A well generally consists of two components: the intake portion, where the water enters the well, and the case portion, where the pipe is installed to keep the drill hole from collapsing. One of the considerations of the case portion is how large the diameter of the well hole should be for the volume of water to be pumped out of the well, and the size of the pump that's going to be installed. In most situations, a groundwater hydrologist or a well driller can come up with a design that will supply the water that you need. To accommodate the casing, the diameter of the drilled well hole is slightly larger than the diameter of the casing. And because the hole is larger than the casing pipe, at the surface there will be an open space around that pipe. To stabilize the geologic materials around the top of the casing and also to keep pollutants out, that open space is sealed with what's known as grout. The intake portion of the well is the part of the well where water enters into the system. The most important part of the intake portion of the well is the well screen. The well screen has openings that are large enough to let water into the well, but small enough to keep geologic materials out. Screen openings are selected based on the particle size of the aquifer. This well screen, for example, has openings of about 0.4 millimeters. It's sized to keep out fine sand, but will let silt and clay through. During what's called well development, the driller will pump out those smallest particles. Well development not only removes the fine-grained material, it also creates a more porous unit immediately surrounding the well screen, since only sand or gravel remain behind. The well screen I have is a small sample made from stainless steel. Cheaper ones are made with PVC screen, like this. They do the same job, just cheaper material. Screen material is selected on the basis of required strength, groundwater quality, and cost. So in places where money is an issue, well, screens can be made out of bamboo or PVC with hand-cut slots. Even after careful design and selection of screen, a groundwater hydrologist might have to hedge their bets a little by putting gravel around the outside of the screen. This is called a gravel pack. Remember, the well hole is going to be larger than the pipe that goes in it. A well driller can take advantage of this open space and feed gravel down around the screen. Essentially, you end up creating an artificial, coarse-grained aquifer immediately surrounding the well screen. That can keep a lot of fine-grained material from entering the well. Lastly, there's the pump. Well pumps are not too different from a sump pump, which goes down in a low spot in the basement where water collects. When that happens, the sump pump accelerates water out of that low spot with an impeller. In a well, the same thing happens. Water that flows through the screen is impelled up the well shaft, but a well pump does not pull or suck water out of the rocks. What a well pump does is remove water from the hole you've drilled. The water flows into the open spaces that a well hole creates. The velocity of well inflow is the velocity of groundwater flow through the rock. The job of a well is not to pull water out of the ground. The job of a well is to provide an open space that will collect water, and the pump accelerates the water out of that space. So when I drill a new well, or if I get my groundwater from a spring, that water is good, right? In the United States, most of the time, the water you get from a new well or a commercially bottled spring water is safe. It's one of the great luxuries of drinking water in the United States. Most of the time, you can assume that it's good quality. But it isn't always. Groundwater is part of the hydrologic cycle. So if there's a component of the hydrologic cycle that is polluted, that will pollute the groundwater. For example, if a river or a lake is polluted and recharging the groundwater, then the groundwater will become polluted too. You should have well water tested regularly, but not everyone does. Even more important is to get water tested when you move into a new house with its own well, or if someone new, like a new baby or a long-term guest, begins living in the house. A guest or a new baby might develop stomach problems from a microbe that doesn't bother the people already living there. What do you get your water checked for? First are contaminants that can be introduced to the well during well drilling. The well driller will disinfect the system once drilling is over, but you still have to check. Second are contaminants that may be leached from the plumbing system, particularly older systems. Lead is a very dangerous pollutant, but there are also contaminants that are more of a nuisance, like iron, copper, or sulfur. Iron and copper come from pipes. Sulfur can be generated in dead spots, which are places in the pipes where the water sits, allowing bacteria to grow. The last group are pollutants that have been introduced to the aquifer that you are pumping groundwater from. Check with local experts on what to look for. In areas where agriculture is a leading industry, you always check your water for nitrates. Nitrates can come from fertilizers, sewage, or even be leached from natural deposits. Of course, we ingest nitrates all the time. They occur in lots of foods and particularly in processed meats. But the problem with nitrates is that they get converted to nitrites and use up a lot of the oxygen in the bloodstream while they're being digested. This is not such a problem for most adults, but for babies, it can be fatal. The syndrome is called methemoglobinemia, or blue baby syndrome. During the digestion of nitrates, the oxygen in a baby's blood supply is used up, resulting in anemia. This is something that's carefully guarded for, and it's one reason pediatricians often recommend bottled water for new babies. Now, sometimes people think that they can solve all water problems by boiling the water. But in the case of nitrates, boiling water makes the problem worse. You can think of nitrates as a salt. The more water is boiled, the more it evaporates, and the more salt is left behind to become more concentrated. Other pollutants that are commonly tested for are microbial contaminants, things that indicate water may be in contact with livestock or septic systems. Inorganic pollutants can come from almost anywhere, including the rocks that make up the aquifer. Fluoride is an example. Moderate amounts of fluoride strengthen your teeth, but too much of it will cause teeth to discolor or mottle. Iron is a common breakdown product of certain rocks, and while iron usually is not a health risk, it can discolor laundry or even hair if high concentrations exist. Manganese is similar to iron in that it will discolor laundry black. Pesticides and herbicides find their way into water systems. They are used ubiquitously, and they are insidious in their ability to work their way into surface waters and drinking water. Certainly, pesticides and herbicides are easy to test for, but identifying their source is frequently very hard to do. Industrial pollution, although very dangerous, is usually something that local experts will have run into in the past. Groundwater is an incredible resource. Bottles containing so-called spring water or artesian water are just groundwater under a more fancy sounding name. It doesn't matter if it's bottled directly from a spring or from a well that goes into the same aquifer. Either way, it might be labeled spring water, but that label does not ensure quality of the water. As I said, you don't realize how much you depend on groundwater until, for whatever reason, you don't have access to it. So don't be afraid to ask questions about the groundwater supplies where you live and what threats, if any, exist to the quality and availability of that resource. And if you have your own water system, do have your water tested. It's worth the time and expenditure. When you do get it tested and you get back a good report, I say drink a toast of water, naturally, to the aquifer that supplies your water.